Hang a pendulum over 3 magnets. Let it go. Watch it swing. Which magnet does it stop at? You cannot predict this. Not because the system is random, not because something is hidden, but because the answer depends on your starting position with infinite sensitivity. Move the release point by a millionth of a meter, and the pendulum lands on a completely different magnet. And when you map every possible starting point to its final destination, what emerges is one of the most beautiful fractals in all of physics. Let me show you how this works. 3 magnets sit on a flat surface, equally spaced, forming an equilateral triangle. A pendulum hangs above them from a fixed point. The bob at the end of the string contains a small magnet, oriented so that each base magnet attracts it. Release the bob from some position, and it swings. Gravity pulls it back toward the center. The magnets pull it toward themselves. Friction slowly drains its energy. Eventually, the bob loses enough momentum and settles directly over one of the 3 magnets. That's the entire physical setup. 3 forces, 1 outcome. But the question of which magnet wins is where everything gets interesting. Let me write the equations. The bob moves in 2 dimensions, so we need its position x, y, and its velocity. Gravity acts as a restoring force, pulling the bob toward the center like a spring. That gives us negative x and negative y. Each magnet pulls the bob toward itself with a force that falls off with distance. For a magnetic dipole, the force follows an inverse 4th power law, but we need to account for the vertical height h between the bob and the magnets. The magnetic force from the nth magnet becomes the vector from the bob to the magnet, divided by the quantity distance squared plus h squared, all raised to the 5/2 power. And damping is simply negative b times velocity, where b is the friction coefficient. Put it all together. The full equation of motion is x double dot plus bx dot plus x equals the sum over all 3 magnets of the magnetic attraction term. This is a system of 2 coupled second-order nonlinear ordinary differential equations. Convert it to 4 first-order equations by introducing velocity components, and you have a 4-dimensional phase space. There is no analytical solution. The only way forward is numerical integration. So let's simulate. Pick a starting point. Set the velocity to 0. Integrate forward in time using Runge-Kutta. The bob swings toward one magnet, gets pulled by another, spirals around, loses energy, and eventually settles. Color that starting point by which magnet captured it. Red for magnet 1, blue for magnet 2, green for magnet 3. Now repeat this for every pixel in a grid covering the plane. Thousands of starting points, each one a full simulation. And when you step back and look at the result, the image is extraordinary. Broad regions of solid color surround each magnet. If you start close to a magnet, that magnet wins. No surprise there. But at the boundaries between these regions, the colors don't form clean lines. They form fractals. Infinitely intricate, endlessly detailed filaments of red, blue, and green intertwining at every scale. Zoom in on any boundary and you see more structure. Zoom in again and there's more. It never stops. This is a fractal basin of attraction, and it arises purely from the deterministic physics of a swinging pendulum. Now here is the part that should genuinely shock you. Pick any point on the boundary between the red and blue basins. Look at a tiny neighborhood around it. You will find points that go to the green magnet. Always. Every single time. This is true for every pair of basins. Every boundary point between any 2 colors is also on the boundary of the 3rd color. This property has a name. It's called a Wada boundary, after the Japanese mathematician Takeo Wada, who first described this topological phenomenon in 1917. Decades before chaos theory existed, Wada showed you could construct 3 open sets sharing one common boundary. The magnetic pendulum does this naturally. 3 magnets, 3 basins of attraction, 1 shared fractal boundary. This means there is no clean dividing line between any 2 basins. Between red and blue, green always intrudes. Between blue and green, red always intrudes. The boundary is a single fractal curve that simultaneously separates all three regions. Before I go further into the mathematics, let me show you another system that produces chaos from simple physics: the double pendulum. Take a pendulum, attach another pendulum to its end. That's it. Two rigid rods, 2-point masses, gravity, and nothing else. The equations of motion come from Lagrangian mechanics. You write down the kinetic and potential energy in terms of the two angles, θ1 and θ2, and their angular velocities. Apply the Euler-Lagrange equations, and you get two coupled second-order differential equations. They're messy. They involve sine and cosine terms of the angle differences, and the mass matrix couples the two angular accelerations together. But the key point is, these equations are fully deterministic. Given initial angles and angular velocities, the future is uniquely determined. Yet watch what happens. Release two double pendulums from almost identical starting positions. For the first few swings, they move in lockstep, perfectly synchronized, as if controlled by the same hand. Then, somewhere around the fifth or sixth swing, one arm flicks a slightly different direction. The deviation grows. Within seconds, the two pendulums are tracing completely unrelated paths. One might be spinning wildly in full revolutions while the other oscillates gently back and forth. This is sensitive dependence on initial conditions. The same exponential divergence we saw in the magnetic pendulum, but now visible as two physical objects moving through real space. And just like the magnetic pendulum, the divergence is not gradual, it is exponential. The distance between the two trajectories in phase space grows as e to the lambda t, where lambda is the maximal Lyapunov exponent of the system. The double pendulum's phase space is four-dimensional. Two angles, two angular velocities. For low energies, the motion is regular and predictable, confined to tori in phase space. But above a critical energy threshold, those tori break apart and the motion becomes chaotic. The transition from order to chaos happens gradually, following the Km theorem. Some tori survive longer than others, creating a fractal mixture of regular and chaotic regions. This is the signature of Hamiltonian chaos, where energy is conserved and there is no damping. The magnetic pendulum, by contrast, is a dissipative system. It has friction. Its chaos lives in the transient behavior, in the question of which attractor captures the trajectory. But both systems share the fundamental property: deterministic equations, unpredictable outcomes. Now, let me show you something remarkable. Step away from physics entirely and enter pure mathematics. There's a purely mathematical system that produces an almost identical fractal to the magnetic pendulum. Take the equation z cubed equals 1. It has three complex roots, equally spaced on the unit circle, at exactly the same angles as our three magnets. Apply Newton's method to find these roots. Start with some initial guess z0, and iterate zn plus 1 equals zn minus f of zn divided by f prime of zn. Each starting point converges to one of the three roots. Color each starting point by which root wins. The result is a fractal that looks almost identical to the magnetic pendulum fractal. Threefold symmetry, intertwined filaments, Wada boundaries. But this one is a Julia set with exact self-similarity, while the pendulum fractal has only statistical self-similarity. Same visual language, completely different mathematical origins. One is a continuous physical system. The other is a discrete iteration on the complex plane. The resemblance is not a coincidence. Both are nonlinear dynamical systems with three symmetric attractors whose basins of attraction must share fractal boundaries. The fractal structure of the magnetic pendulum depends critically on one parameter, the damping coefficient B. With heavy damping, the bob barely swings. It falls almost directly to the nearest magnet. The basins are large, smooth, and their boundaries are relatively simple. Lower the damping, and the bob swings further. It visits more magnets before settling. The boundaries become more complex. More filaments appear. the fractal dimension of the boundary increases. The fractal dimension is measured using the uncertainty exponent. Take a starting point, perturb it slightly. If the perturbation changes which magnet wins, that point is uncertain. The fraction of uncertain points scales as epsilon to the power alpha, where alpha is the uncertainty exponent. The fractal dimension of the boundary is 2 minus alpha. For light damping, B equals 0.1. The boundary dimension is approximately 1.4. Heavily damped, B equals 0.2. The dimension drops to about 1.16. Simpler boundaries, lower dimension. At zero damping, something qualitatively different happens. The pendulum never settles. It swings forever, never choosing a magnet, tracing a trajectory that fills a region of phase space ergodically. The fractal basin structure doesn't exist because there are no basins to fall into. The system is Hamiltonian, energy is conserved, and the pendulum is trapped on an energy surface for eternity. Damping is what forces a choice. Friction is what creates the fractal. Without dissipation, there is no decision. With it, every initial condition must eventually commit to one attractor, and the geometry of that commitment is fractal. And here is the physical reality. You can build this system: 3 disc magnets on a tabletop, a magnetic bob on a string hanging from a frame above. Let it go. It swings chaotically, spirals, hesitates between magnets, and eventually stops. Release it from what seems like the same spot, and it may choose a different magnet every time. Not because of randomness, but because your hand cannot reproduce the same initial condition twice. The fractal basin boundary passes through your release point at every scale. Any finite precision in your starting position straddles regions belonging to different magnets. This is the same deep paradox we encountered in the Lorentz system and the logistic map. Determinism does not imply predictability. The magnetic pendulum obeys Newton's laws exactly. Every force is known. Every equation is specified. Given perfect initial conditions with infinite decimal places, the outcome is uniquely determined for all time. But perfect initial conditions do not exist in the physical world. And in a system with fractal basin boundaries, any imprecision, no matter how small, can change the outcome entirely. The fractal guarantees this. At every scale, the boundary is there, threading between your measurement and a different future. 3 magnets, 1 pendulum, an infinite fractal encoded in the question, where does it stop? The answer is determined, but it is forever beyond your reach.